Semigroups and their representations. Lecture 1. Semigroups and monoids. Let us start with the definition of a semigroup. Definition: a semigroup is a pair which consists of a non-empty set, let's say S, and an associative binary operation on S, which for the moment we will denote by an asterisk. Remark 1. Associativity of this operation means that for all elements A, B and C in S, taking the operation between A and the outcome of the operation applied to B and C, we will get the same outcome as we get when we take the operation for the outcome of the operation applied to A and B, and then with C. Remark 2. This operation asterisk is usually referred to as multiplication. However, in specific examples, we might have some different operations, for example, addition. Due to the associativity of our operation, the product expression A1 asterisk, A2 asterisk, and so on, asterisk AK, is well defined as an element of our semigroup in the sense that it does not depend on the bracketing of this expression. Remark 3. For brevity, we will often denote our operation by dot and simply write AB instead of A asterisk B or A dot B. Also, if our operation is clear from the context, we will just say that S is a semigroup without saying that the semigroup is a pair consisting of S and the operation. Here are some starting examples which mostly come from numbers. So if we consider the set of all positive integers with respect to addition, this is a semigroup, because adding positive integers we get positive integers and addition is associative. Similarly, the set of all non-negative integers with respect to addition is a semigroup, or the set of all integers with respect to addition is a semigroup. Similarly, the set of all positive integers with respect to multiplication is a semigroup, because multiplying positive integers we get a positive integer, and multiplication is associative. Similarly, the set of all non-negative integers with respect to multiplication is a semigroup, and the set of all integers with respect to multiplication is a semigroup. We have similar examples of the additive semigroup of all real numbers, or multiplicative semigroup of all real numbers, and similarly for rational, complex numbers, and so on. Also, we can take the set of all non-zero integers, and this will be a semigroup with respect to multiplication. Similarly for real, rational, or complex numbers. Now let us talk about identity elements. So let S be a semigroup with an operation asterisk. Definition: an element E in S is called an identity element, provided that E times A is equal to A times E and is equal to A for all elements A in S. For example, 0 is an identity element in the semigroup of all integers with respect to addition, and 1 is an identity element in the semigroup of all integers with respect to multiplication. Proposition: if E and E prime are identity elements of S, then E is equal to E prime. Proof: on the one hand, the product of E and E prime is equal to E prime, because E is an identity element. On the other hand, the same product is equal to E, because E prime is an identity element. This implies that E is equal to E prime. Consequently, if a semigroup contains an identity element, this identity element is unique. So for example, 0 is the identity element in the semigroup of all non-negative integers with respect to addition, while the semigroup of all positive integers with respect to addition has no identity element at all. Now we can define the notion of a monoid. Definition: a monoid is a triple which consists of a semigroup consisting in turn of a non-empty set S and the binary associative operation asterisk on S, and an identity element E in this semigroup. For example, we have the monoid, the additive monoid of all non-negative integers with respect to addition, where the identity element is 0. Similarly, we have the additive monoid of all integers, where the identity element is 0. We have the multiplicative monoid of all positive integers with the identity 1, and similarly the multiplicative monoid of all non-negative integers with the same identity, and the multiplicative monoid of all integers with the same identity 1. Remark: given a semigroup S, asterisk, we have the associated monoid S upper 1 dash 1, which is constructed as follows. So if the original semigroup S has an identity element, we call this identity element 1, and then set that S upper 1 is equal to S, and the new operation is the old operation, and then we have the monoid S upper 1, the new operation, and then our identity element 1. If the original semigroup S does not have any identity element, then we take an external element 1, we add it to S, so we define S upper 1 as the union of S with this new element 1, and we define the new operation as follows. So it coincides with the old operation for elements in S, and the new element 1 acts as the identity. So if we multiply anything with 1 on any side, we get our anything back. And it is easy to check that this new construct is indeed a monoid with identity, this new element 1. So each semigroup can be easily turned into a monoid by adding an external identity element. Now let's look at further examples. We start with transformations. Let X be a non-empty set. Consider the set T of X or T sub X of all functions from X to X. Functions are the same thing as maps from X to X. On this set we have the binary operation of composition of functions, which is usually denoted by such circle. So f after g, that's f composed with g, the value of this composition at an element I in X is equal to f of g of I. And we know that this composition is associative, and hence this set is in fact a semigroup. Moreover, we have the identity function on X, which is defined in the following way. So this identity on X applied to any element I of X gives us I, and this identity function is an identity element in the semigroup Tx. Therefore, Tx is in fact a monoid with identity, this identity on X. This monoid is called the full transformation monoid or the full transformation semigroup on X. In the case when X is the set 1, 2, and so on n for some positive integer n, then the semigroup Tx is usually denoted by Tn. Next example, the semigroup of all words. Let A be a non-empty set, which we call an alphabet. Denote by A upper cross the set of all non-empty words over A, that is, expressions of the form A1, A2, and so on AK, where K is a positive integer and all AIs are elements in A. So here K is called the length of this word. We can concatenate the words, so write them one after the other. So if we have a word A1 and so on AK, and B1 and so on BM, we concatenate them, and we get the word A1 and so on AK, B1 and so on BM. And this concatenation is obviously associative, hence our set, with respect to concatenation, forms a semigroup. Next we can consider the empty word epsilon, which has no letters, so it's the empty word of length 0. By definition, if we concatenate epsilon with any other word, we get our word back. This means that if we set A asterisk to be the union of A cross with our empty word epsilon, we get the monoid, which consists of all words, including the empty word, with respect to concatenation and with the empty word as the unit element. Next example is a semigroup of all matrices. So let K be a commutative ring and n a positive integer. Consider the set mat sub n times n of K of all n times n matrices with coefficients in K. This is a semigroup with respect to matrix multiplication because matrix multiplication is associative. It is even a monoid as the identity matrix is a unit element. Note that the set of all n times n matrices with coefficients in K is also a semigroup and even a monoid with respect to matrix addition, and here the identity element will be the zero matrix. Now let us briefly discuss commutative semigroups. Recall that a binary operation asterisk on a set S is called commutative, provided that A times B is equal to B times A for all AB in S. And then a natural definition, a semigroup S is called commutative, provided that the operation on this semigroup is commutative. For example, all arithmetic semigroups like integers with respect to additions or rational numbers with respect to multiplications and so on, they all are commutative because addition and multiplication of numbers is commutative. Example 2, the full transformation semigroup on a set X is commutative if and only if the set is a singleton. Example 3, the semigroup of all n times n matrices over a commutative ring K is commutative if and only if n is equal to 1. Remark, commutative semigroups are also called abelian, and similar terminology is used for monoids. Now we can talk about zero elements. Let S be a semigroup. Definition: an element Z in S is called a zero element, provided that multiplying this element with any other element in the semigroup on any side gives us our element Z back. For example, the element 0 is the zero element of the multiplicative semigroup of all integers. Example 2, the additive semigroup of all integers doesn't have any zero element. Proposition: if Z and Z prime are two zero elements of S, then Z is equal to Z prime. Proof: on the one hand, the product of Z and Z prime is equal to Z because Z is a zero element. On the other hand, the same product is equal to Z prime because Z prime is a zero element. So therefore, Z is equal to Z prime. So this means that we can speak about the zero element of a semigroup if such an element exists. Now we can discuss the notion of a subsemigroup. Let S be a semigroup. Definition: a non-empty subset T of S is called a subsemigroup, provided that the product of two elements in T belongs to T. Remark, any subsemigroup has the natural structure of a semigroup with respect to the restriction of the operation from the bigger semigroup S to this subset T. For example, we have inside the additive semigroup of all integers, we have a subsemigroup of all non-negative integers. That's because adding two non-negative integers, we get a non-negative integer. Example 2, if X is a set, then if we look at the full transformation semigroup Tx on X, inside it we had the subsemigroup of all bijective transformations from X to X. If we compose two bijective transformations of X, we get a bijective transformation. So the set of all bijective transformations, which is usually denoted by S sub X, is a subsemigroup of Tx. Example 3. If K is a commutative ring, then we can consider the set of all invertible n times n matrices with coefficients in K, and this will be a subsemigroup of the semigroup of all n times n matrices with coefficients in K. And example 4, A upper cross is a subsemigroup of A asterisk. Next we discuss the notion of a submonoid. Let M be a monoid with identity E. Definition: a submonoid of M is a subsemigroup N of M which contains the identity E. For example, If you look at the monoid of all integers with respect to addition, then the subsemigroup of all non-negative integers with respect to addition is a submonoid, because it contains the identity element 0. However, as an example 2, the subsemigroup of all positive integers with respect to addition is not a submonoid of the monoid of all integers, because positive integers do not contain the identity element 0. Example 3. Let us look at the multiplicative monoid of all integers. In this multiplicative monoid, we have a subsemigroup consisting of the element 0, because 0 times 0 is 0. Note that 0 is the identity element of this semigroup. However, this is not a submonoid of the multiplicative monoid of all integers, because it doesn't contain the identity element 1 of that monoid. So in this example, we have a monoid which is a subsemigroup of a bigger monoid, but which is not a submonoid. So it's not correct to say that a submonoid of a monoid is a subsemigroup which is in itself a monoid. To be a submonoid, it should have the same identity element as the original monoid. In order to discuss further examples of semigroups and monoids, we need to discuss the notion of a partial transformation. So let X be a non-empty set. Definition: a partial transformation of X is a function, say alpha, from some subset Y of X to X. The set Y is called the domain of alpha and denoted by dom of alpha. So for example, any transformation of X is a partial transformation of X with domain X. Example 2, if we pick any pair of elements I and j in X, we have the partial transformation delta ij, which is defined only on I and which sends I to j. Example 3, we have the partial transformation 0 sub X, which has domain the empty set, and so it's not defined at any element. Notation: the set of all partial transformations of X is denoted by Pt of X or Pt sub X. And in the case when X is the set 1, 2, and so on up to n is a positive integer, then the corresponding Pt sub X is denoted by Pt sub n. Here is an example of Pt sub 2, so that's all partial transformations on the set 1, 2. So we list all of them using the two-line notation. So in the first row we have the domain, which is written in the natural order, and then in the second row we list the values of our transformation on the elements of its domain. So we start with an element which sends 1 to 1 and 2 to 2, and it is defined on the whole set 1, 2. Next we have the element which sends 1 to 2 and 2 to 1. It is defined on the whole set. Then we have the element which sends 1 to 1 and 2 to 1, with the domain the whole set, and the element which sends 1 to 2 and 2 to 2. Again, the domain is the whole set. Then we have the element with domain 1, which sends 1 to 1. Then domain 1 and 1 goes to 2. Then domain 2, 2 goes to 1. Domain 2, 2 goes to 2. And then the element 0, which is not defined on any element. So the domain is the empty set. Altogether we have 9 elements, and 9 is 3 times 3. And so the cardinality of Pt2 is 3 times 3, because for each element in the original set 1, 2, we can choose the image of each of these elements to be either 1 or 2 or undefined. So we have 3 choices for 1 and 3 choices for 2. Altogether we have 9 elements. Partial transformations can be composed. So let's define composition of partial transformations. So let alpha and beta be 2 partial transformations on X. Consider the set Y, which is the set of all elements I in the domain of beta, such that beta of I belongs to the domain of alpha. So we define the composition of alpha after beta as the partial transformation of X with domain this set Y, such that alpha after beta applied to an element I in this domain is defined as alpha applied to beta of I. And this is well defined due to the definition of y. And we take this formula for any I in y. For example, here is the composition of two elements in PT4. So our first element sends 1 to 2, 3 to 4, and 4 to 1. And then after it, we take the partial transformation, which sends 1 to 1, 2 to 2, and 3 to 2. So their composition sends 1 to 2, so 1 goes to 2, 2 goes to 2, and 4 to 1. 4 goes to 1, 1 goes to 1. We can also try 3. 3 goes to 4, but here 4 is not in the domain, so the outcome will not be defined on 3. Note that we compose functions from right to left as usual, so the right function is applied first and then the left function. And here is the composition of the same elements in the opposite order. So 1 goes to 1, 1 goes to 2, so 1 goes to 2 in the outcome. 2 goes to 2, but this is not defined on 2, so the outcome is not defined on 2. 3 goes to 2, this is not defined on 2, so this is not defined on 3. And the first transformation is not defined on 4, so 4 is not in the domain. So this is how we compose partial transformations. And the claim is that the composition of partial transformations is associative. Proof: let alpha, beta, and gamma be 3 partial transformations on X. We know that the composition of usual transformations is associative, and composition of partial transformations is defined via composition of usual transformations when we restrict it to the domain of the transformation. So in order to prove the proposition, we need to argue that the domains of alpha after beta after gamma is the same as the domain as alpha after beta after gamma. And it's easy to see that both of these domains coincide with a set of all elements I in X, such that gamma of I belongs to the domain of beta, and beta of gamma of I belongs to the domain of alpha. And this completes the proof of the proposition. Since composition of partial transformations is associative, we can speak about the semigroup of all partial transformations of X. So that's the semigroup PTX with respect to the composition of partial transformations. It is very easy to see that the identity transformation on X is an identity element of PTX. Therefore, PTX is in fact a monoid. That's the monoid of all partial transformations of X. Clearly, full transformation of X form a submonoid of all partial transformation of X. Moreover, if X is finite, then the complement of Tx inside PTX is a subsemigroup of PTX, but it is not a submonoid because it doesn't contain the identity on X. Finally, let us discuss the notion of a codomain and rank. Let alpha be a partial transformation on X. Definition: the set alpha of I, where I is an element in the domain of alpha, is called the codomain of alpha and denoted codom of alpha. And the cardinality of the codomain of alpha is called the rank of alpha and denoted rank of alpha. For example, if we look at the following element in PT4, so it sends 1 to 2, 3 to 1, and 4 to 1. It has domain 1, 3, 4, codomain 1, 2, and rank 2. The element 0x has as a domain the empty set, as the codomain the empty set, and rank 0. And the identity on X has X as a domain, X as a codomain, and rank the cardinality of X. It's a nice exercise to check that the rank of the composition of alpha and beta is at most the rank of alpha and is at most the rank of beta. So it's less than or equal to the minimal between the rank of alpha and the rank of beta. Using these notions, we can define the notion of a partial bijection. So an element alpha in PTX is called a partial bijection if it is injective on the domain of alpha. The set of all partial bijections on X is denoted by ISX, or IS of X, or ISN, when X is 1, 2, and so on up to n. So for example, any usual bijection from X to X is of course a partial bijection. Example 2, any partial transformation with a singleton domain is a partial bijection. Example 3 is the 0 element 0 sub x is a partial bijection. And the final example, let's look at two elements in PT4. The first one sends 1 to 2, 3 to 3, and 4 to 1. This is a partial bijection. But if you look at the element which sends 1 to 2, 3 to 2, and 4 to 1, this is not a partial bijection because two different elements 1 and 3 in the domain are sent to the same element 2 in the codomain. Proposition: Is of x is a submonoid of Pt of x. And the terminology Is of x is called the symmetric inverse monoid or the symmetric inverse semigroup on x. Proof: clearly the identity transformation on x is a partial bijection, so it belongs to Is of x. So we only need to argue that composition of partial bijections is a partial bijection. From the definition, this reduces to the observation that composition of injective maps is an injective map. And so this proves our proposition. It's a nice exercise to check that the zero partial transformation, whose domain is the empty set, is the zero element in the monoid Isn, and in fact in the monoid Ptn, and that the cardinality of Isn is equal to the sum over all k from 0 to n choose k squared times k factorial. So let's make the following summary. For a set X, we have the following four classical transformation monoids on X. The monoid of all bijections from X to X, that's in fact a group, so that's a symmetric group Sx. The full transformation monoid Tx. The monoid of all partial transformations of X, so that's Ptx. And the symmetric inverse monoid Isx. And these monoids are embedded as follows. So Sx is the smallest one. That's a submonoid of both Tx and Isx, which are not embedded into each other, so they're unrelated. And all these monoids are submonoids of Ptx. Some additional problems and questions at the end. Problem question 1. Check with all details that S upper 1 dash 1 is a monoid. Problem question 2. Let S be a semigroup and Z not in S. Shows that S union with Z has a natural unique structure of a semigroup with 0 Z such that S is a subsemigroup. So we can always start with a semigroup and add to the semigroup an external 0 element. Problem question 3. Determine all subsemigroups and all submonoids of both T2 and T3. Problem question 4. Prove that the cardinality of Ptn is equal to n plus 1 to the power n. And problem question 5. Prove with all details that if x is finite, then the complement to Tx inside Ptx is a subsemigroup of Ptx. Thank you very much and see you next time.